Welcome back to Forecast Lab. Let's take a look at that weather map for this afternoon. Heading into the middle of June, we've got a frontal system through the Midwest and extending all the way down into Texas. Unseasonably cold weather in places like Woodward, Amarillo. They're down in the mid-60s when they should be seeing well over 90. Got a pretty good squall line running through western Arkansas down towards northeast Texas. Some of that cold air is hung up in Colorado, keeping the temperatures down around Denver and Colorado Springs, and then we see that extend back into the Great Basin as a stationary front. Temperatures in the desert southwest are fairly warm, up to 97 at Phoenix there. And then we take a look at the East Coast, and yeah, it is warm, except when you get up towards New York City, Albany, and New England. Temperatures only down in the 70s in that region. And then an old stationary front through the Carolinas into the Atlanta area associated with a lot of thunderstorm activity. In the Alaskan and Pacific region, some more cold air coming into British Columbia. And it was only about a year ago that we had those record hot temperatures. We are certainly glad we don't have that this time of year. 50s and 60s instead of hundreds and 110s. Up in Alaska, some more cold air working its way into the Brooks Range all the way to the Northwest Territories. Temperatures down in the 60s. That's a little cooler than what we had on Monday. But if you take a look out in Quebec and Labrador, it is warming up in that region. 77 right there. Almost 80 degrees, starting to make its way up towards the Arctic Circle. And then going down to Ontario, another bit of cold air working into the Great Lakes region, showery weather, and showers associated with air mass modification over that muskeg region of Ontario. Let's take a look at the upper air patterns because to a large extent this does affect our weather even in the summertime. Starting out, we see weak flow across much of the country. Up to the north, yeah, there's some 100-knot winds, mostly around the Great Lakes, but out west, light winds, mostly 50 to 60 knots and below. This is up at about 34,000 feet. The flow overall is westerly, a little bit deformed down in the Baja California area due to a cutoff flow in that region. But let's see the changes over the next few days. Trough moving into the northeastern U.S. and a ridge building out west. And there it is taking shape across Montana and Wyoming. Broadens out and extends into the Great Plains area. And it looks a little bit more amplified, especially in the southwestern U.S., where it almost closes off across Southern California. So we're probably going to see some very warm temperatures in that region. And it also looks like, if you look closely at these wind plots, this almost paints out a closed circulation over West Texas. So it could be some warm weather there going into the weekend. Then Saturday and Sunday, some of that ridging extending over Texas, prolonging the hot temperatures, but some easterly flow starting to show up in the Gulf, and that tends to be kind of a late summer pattern when it's well established. But here, yeah, that's going to be a closed circulation. There's the high across Texas and Louisiana, so probably remaining quite hot going into Sunday. Large trough coming into the West Coast region, and it looks like there's some amplification of the patterns. When that happens, the weather gets more interesting. You get more transport of heat north and south, and of course that increases the mean baroclinicity of these weather systems, and overall that shifts things towards a more energetic weather pattern. So that's certainly going on next week. Another deep trough working into California. That's unseasonably strong. So that's going to be late next week, 18th. And that is about all we have there. We close it out with almost an omega block. Maybe not quite, but almost. but still significant ridging through the central U.S. Let's take a look at the records. This is a good measure of how crazy the weather is. Not too bad for today, 100 degrees at Austin. If that hits 100, that will break the record by 1 degree. There's how it looks for tomorrow. Garden variety heat once again in Texas. Then things get worse for Friday. Lots of heat across the desert southwest, Phoenix, 113, 109 at Vegas, and 105 at Sacramento. This is definitely what we don't need. I mean, come on, this is ridiculous. So if this is an indication of climate change, at least it's predictable in the fact that it's always hitting the same areas. For Saturday, the heat continues on the southwestern U.S., 109 at Vegas, and the heat gets a little worse in Texas with 105 at Austin. And for Sunday, more of the same, hundreds all the way from Tyler, Texas to Roswell, New Mexico, and there's a 113 right there at Phoenix. There's Monday, and there's Tuesday. Looks like maybe the heat is shifting east a little bit into the Tennessee and Kentucky area. So let's do something a little bit different. You know, we've never really been a weather news program. We kind of started out as an educational channel using current weather, and I guess we kind of need to get back to that just a little bit. So let's take a look at the weather we have going on right now before we start into that. A decaying storm complex across Arkansas and Oklahoma. Looks like a lack of new convective cells. Don't have this kind of activity. That's new cells in Alabama. And looks like some fairly fresh cells going up across the eastern U.S. There's how it looks on the SPC mesoscale analysis. Not showing much convection there. Let's take a look at GR level 2 real quick. Decaying convection, any new convective elements down there around Arkadelphia, but a large trailing stratiform region. And there's some of the newer convection in Alabama where strong heating is taking place. That convection is moving west to east. Let's check out the SPC experimental mesoanalysis. And before I do that real quick, let me show you this boundary. That's pretty neat. That was probably put out by this storm, generating a cold pool that is surging to the northwest. So this is certainly not a major severe weather day, but we can take a look at some of the products. At the very top left, you have observations. There's some other panels for surface, upper air, thermodynamics, and so on. Let's take a look at the surface observations. Well, you're probably familiar with that. Temperature in the top left, dew point in the lower left. So we probably don't need to go over that too much. Printable surface map, I'm going to skip that there. Visible satellite, I would really recommend using a tighter sector. This is probably not the best way to go about doing that. You can get to that to a certain extent by using the sector selection, and you'll get something that looks like, I don't know. Yeah, there we go. But I would strongly recommend using Ecology to Page, because with visible satellite, it's very important to get in there and look at things up close, and you want to use any overlays available for referencing the data. For example, county overlays or U.S. interstates. So use what you can to get a picture on what's happening. And here we can clearly see some sort of outflow boundary. Well, it's actually probably the front there that we analyzed earlier. That does not quite as well show up because we're pretty zoomed out. So you can use that for just a first glance at what's happening. Radar base reflectivity, that's obviously not composite reflectivity. Base reflectivity is not necessarily the 0.5 degree scan, but it implies that you're getting one of the base products from the next red unit, which is going to be your reflectivity, velocity, spectrum width, and the dual pole data as well. VAD profiler data. I'm not exactly sure what that is. It doesn't seem to do anything. I know the profiler network was decommissioned, and that leaves us with some of the university and research profilers, and of course the VAD data from the WSR-88D. Let's go into the surface dropdown. MSL pressure and wind. Yeah, that's your sea level pressure every 2 millibars. Your surface winds. So that gives you kind of an initial look at what's happening. West to southwest flow across the southeastern U.S. Temperature, winds, dew points, we get more into the basic measures of heat and moisture. The colored solid lines, those are going to be your temperature. The dashed blue lines, kind of hard to see in here, that's going to be your dew point. And those values are shaded. And then, of course, we have the black lines for sea level pressure. So what does this tell you? It kind of varies on the weather situation. You can isolate the fronts kind of like that by going on the tropical side, on the warm side of the gradient. You can see right in here, those are isotherms. That's indicating a thermal gradient. So anywhere on the warm side of that, it's very possible that there's a frontal boundary. It could be an outflow boundary as well. But that can help you to kind of establish where these things are. And then the shading, I would probably not look too much at these dashed blue lines because it's kind of like a big plate of spaghetti. But the shading, I would go by that, and that identifies where your moist air mass is, your higher dew points, but that's strictly a measure at the surface, and it doesn't really give much character as far as the depth of that moisture. Then we have moisture convergence. So that's basically where the winds are converging and superimposed with high levels of moisture. The green lines, those indicate mixing ratio. Those are roughly proportional to your dew point. So you can kind of use that as a proxy for dew point. So the blue lines indicate where your moisture convergence is taking place. That tends to correlate with a higher chance of convective weather. That's not going to be your best measurement. You know, this was kind of seen as a holy grail for finding storm initiation back in the 90s. But as it turns out, this is a derivative field. Derivative fields are only as accurate as the original data itself. And as you start putting more and more quantities together, you're more likely to fail because it's making assumptions of what's happening in the atmosphere. Theta E advection, I actually like this one because theta E is how far your lifted parcel is to the right side of the diagram. And of course, the farther over we have this lifted parcel to the right, the more cape that we get when we measure that against the environmental parcel on the left there. And that also comes with an increased chance of initiation. So it does tend to be a useful parameter, not so much in the summer when it's noisy like this, but a lot of times when you have severe weather on the Great Plains, where you have strong return flow and good cyclogenesis, you will find axes of high theta E or noses of high theta E, and those tend to represent areas where severe weather can be expected. So not so useful today, but on other days, I certainly like using it. Mixing ratio and theta. Now, theta is not theta E. Theta is basically your air temperature reduced to 1,000 millibars, which is just above sea level. So we take a look at that. This is basically an isotherm plot, and it will correlate very, very closely with isotherms if the ground is perfectly level. So you're going to get different results out there in the western U.S. Let me go to the southwest U.S. and bring up that plot. Well, you can certainly see the gradients along the coast, but inland, very high theta values. Now, you'd probably think that the hottest temperatures would be around Phoenix, Tucson, Yuma, and Las Vegas, but we don't really see that. The highest values of theta are in Utah and Nevada And that's because of the very, very strong heating, even in those elevated regions of Nevada and Utah. Probably much more heating than what we have in the southwestern U.S. So if you actually brought this air down to sea level, it would be probably in the 120 degree range. So to a certain extent, this can be useful for finding fronts in the mountains. And I do see kind of a gradient right in here. And that does correlate somewhat with this front. Might need to refine the placement a little bit. I think it probably actually goes back in here, since this is indicating cooler air in north central Nevada. Then in the Great Plains around frontal zones, you can certainly see the frontal gradient right there, the thermal gradient. Cooler temperatures back behind it, falling off to about 300 Kelvin across Amarillo. And of course, we also have the mixing ratio on here, which again is similar to dew point. We can find some pooled moisture right here back behind the front that's supporting the potential maybe for some isolated storms in that region. And then south of the frontal boundary, quite dry. We can also see the dry line. We go from the lack of shading, the light blue shading, to green shading along Interstate 35. And of course, the theta temperature does come up out there in the hot air because of the very strong heating and the low specific heat of dry air. And going into this menu right here, we get into some more complicated kinematic measurements. Some of these deal with frontogenesis. I'm going to only focus on the two that I use regularly. One is the velocity tensor magnitude that does tend to paint out where the fronts are to a certain extent. The shading is what I go by. Of course, it gives you theta to help pinpoint the front a little bit better. We use theta in a similar manner on this chart to what I showed you just a minute ago. But the shading, that kind of identifies where fronts could be. Maybe another one right there. And maybe a reinforcing shot. That could be outflow back there around Childress. And then divergence and vorticity. Now that's very helpful during severe weather events. The closer we can get to good point convergence, that's going to focus development in a very specific area and help produce discrete supercells instead of linear storm complexes and MCSs. So I do like seeing this pile up of convergence on a storm day when I'm looking for severe weather. What I don't like is these long elongated areas, and I think that's contributed to a lot of failures of severe weather events back last May, back around the 25th to 30th. So when you spread out that convergence, you get numerous cells going up, especially if the capping is weak, and you end up with a lot of cell interaction and a common cold pool driven convection, and a tendency towards MCSs. Deformation and axes of dilatation, you can use that to a certain extent as well to find fronts. But I do find the velocity tensor magnitude to be a little bit more helpful. 2-hour pressure change, that can help track your mesolow development. Of course, you can get this directly from the METAR data and tracking METAR trends, but this comes from the rapid refresh model, so it's picking up a little bit more on the mid-level, the mid-tropospheric details, and it tends to be a little less noisy. So you can use that to augment your diagnostic process and look at the trends and the forecast to kind of watch the movement of those areas. So this here, you can see that this large area of pressure falls is on the move, and that suggests that this couplet here is dynamically forced. 3-hour temperature change. Never really had a big use for that, but that can kind of help track your thermal advection. 3-hour dew point change. Yeah, that's helpful for seeing if your environment is moistened up, especially at the nose of your return flow coming in from the Gulf. 3-hour 100 millibar mixing ratio change. Now, I believe that's going to be a mixture of the lowest 100 millibars. I don't think that's 100 millibars off the surface. I think that's a layer computation, and that kind of will give you an idea if you're eroding the moisture, how fast that's going on, and see how fast that's being replenished through advection. And then theta E change, that goes back to your theta E plot, and that can tell you if advection is contributing to an increase in that theta E and helping to make initiation more likely. All right, then we get into the upper air analysis, 925 millibars. That's going to be the layer about 2,000 to 3,000 feet off the ground. So that's going to be right within your moisture field. That gives you some information on how deep and rich it is. And of course, you got the plots here, the wind plots, so you can track low-level jets. Those will show up very well at 925 millibars in the eastern U.S. and the Great Plains. 850 millibars, that sometimes gets above the moisture, not always, but that'll give you information on the depth. If you've got a lot of moisture in place at the surface, but not at 850, that tells you that the moisture is rather shallow. And of course, the wind plots again will give you information on where the low-level jet is. The low-level jet is often strongest at 850 millibars. Version 2, I've never really used that. I guess that's a little bit less cluttered. 700 millibar analysis, that's getting into your cap. The cap does not always coincide with 700 millibars, but it's usually pretty close. This is up at about 10,000 feet. You can see that the temperature increases as you go west. We go from 10 to 16 Celsius. Now, of course, we often see that because of the very strong heating in the desert southwest, and the terrain is higher, so it's rising up to meet the 700 millibar level. But when we see these plumes of thermal ridging coming out of the desert southwest, that's usually associated with strong capping overrunning the tropical moisture down beneath. And you can look at the wind to see just how fast it's coming in. Let's see, what else do we have? 500 millibar analysis, that gets into your mid-troposphere. That's going to be near your mid and upper level dynamics. So what we have here is temperature. So where the temperatures are cooler, you're going to have the potential for more instability. And of course, you can see the wind here that gives you an idea of how baroclinic your atmosphere is. We got 40 knots up here in Kansas, very weak conditions in the Texas region. So the air mass is definitely more baroclinic as you move north. And we can also see the mid-level high right here over Louisiana. 300 millibars, of course, we deal with that very regularly on these forecast lab segments that shows your jet stream. Let me move up there. You can get a look at that. The shading is going to be your ice attacks. So your jet located right there across Des Moines and heading up towards Fort Wayne, Indiana. Yeah, there's a better look at that right there. And the magenta, that's going to be your divergence. So it's trying to solve for divergence, and where you have a lot of that, that usually suggests upward motion, upper forcing. So here it's been corrupted a little bit by this convection. Same thing in Arkansas. So you don't want to nitpick too much around precip areas, but out ahead of that, you can see some dynamic forcing taking place across the northeastern U.S. Then we have these other products, and I'm realizing it's taken us a long time to work through this. So this might be a good place to stop for now. But those are some of the most helpful basics there. I guess we might have to do a hour-long program going through all of these. So maybe that's something we'll try to do here in the next couple weeks. Okay, so that's probably a good place to stop for now. Hope you enjoy the rest of your Wednesday evening. We'll see you back here on Friday, and maybe we'll go through some more of those SPC products. Take care, and we will see you in a couple days. Bye-bye.